Yes, please continue. Fine.
Okay, so
Lavish, you can just share
I
your
guess we can start. I'll just check if people have joined online as well.
You can share your screen, Lavish.
Okay.
Okay. You can just share
Not
your
people online. Okay. Just check if people have joined. So you have gone through the assignment, right? I hope everyone has gone through the assignment. So there are two parts. One is on concentration inequalities, basically the Chernow bound, and the other one is the multi-arm bandit problem, where you will have to code two algorithms. One is explore, then commit, and second is the UCB algorithm, upper confidence one. So if you have any doubts, we can go through them directly, or I can also go through uh, the assignment as well, like basic tutorial, which is there. Hello? No, no, no. Yeah, thank you. Yeah, thank you. Okay. So, do you have any doubts in question one? Are there any doubts in question one? You can use that. It's not. You can also do that. You can write your code from scratch, but make sure you submit it in a Jupyter notebook. Yeah. For the first part, there is no base code. It's just the instructions are there. So it's just that there are instructions there, and it's for the first part, it's like it's nothing. You can just start write your own. So basically, I'll just show you. So this is part A. So just make sure you include your name and roll number, and uh, and that's it. I think it's just the code. So if you have just the code, that's fine. Yeah. So, okay, let me just briefly go through this. So what the first part demands is, it basically asks that we verify this. We verify this inequality through simulations. So we have to run Monte Carlo simulations for this experiment. So for this, what we have to find out, it's what it says. It says that the probability of sum of IIT copies of n random variables is less than this expression, e to the power minus n. So how do we then find a measure of this probability? So for finding this measure of probability, what we have to do is we have to run multiple experiments and then check on how many cases it satisfies. Yeah. For each value of small n, we'll run 500 experiments and then check. Yeah. So what we'll do is we'll sample. So for sampling, we can directly use this NumPy. And in NumPy, sampling is very straightforward. So we just do np.random.normal. And the arguments are mean. The first argument is the mean. Second argument is the standard deviation. The third argument is number of samples that you want. So basically what this will do is it will sample from n0, 0.1, a normal distribution with mean 0, standard deviation 0.1, and it will take 10 samples. So we can basically check if the mean is greater than or less than some epsilon for them. This is one experiment. Now we can repeat this n number of times, and then we can find out for those n how many times it is greater than epsilon. And that will give us the measure of probability. And then we can also calculate this based on n, epsilon, and also sigma square. And then we can compare these two. And basically it demands you to plot this for multiple values of n. So we can do that. And also we can plot a curve for this function. So what we'll get is basically so what we'll get is the curve follows something like this. And then when we simulate, so for a particular n1, there is n2, we'll basically have points here. So we'll have multiple points. I think this is quite straightforward. If you have any further doubts, we can go through this. You can try this if you have laptops. You can like just now also go ahead and try this. And if you are facing any issues, we can. So Monte Carlo simulations is basically if you just take say n samples here, then you can only calculate this mean, right? You can calculate this x, and that will give you if x is greater than epsilon or not. It won't give you a probability. So Monte Carlo simulation is you run it for multiple experiments and then check in how many experiments through Monte Carlo experiments, simulations, you can do a probabilistic analysis, or you can calculate the probabilities. So if you don't do Monte Carlo, you will do it for only one, and then you cannot calculate probabilities. So Monte Carlo is doing multiple experiments. So you do multiple experiments, and through that multiple experiments, you form your sample space. And in that sample space, you can check, you can find probability through that sample space. Yeah, those who have joined online can also try to do this. So basically, if I just sample, it's giving me 10 samples centered around 0 with this deviation. So this is like one set of xi's, x1 to xn, which I've got realizations of them, and then I can take a mean of it. And if I put it in a for loop, then I can get basically various means. And then I can also add a condition that if this is greater than epsilon, some number, whatever epsilon I choose or is given in the question, and if this is satisfied, then I can update a count. And using that count, I will get the probability. I can calculate the probability. And that's what I want. That's what I want. I want an empirical estimate of the probabilities. Any doubts? Okay. So I think this is fine. This part is okay. You guys can go ahead and try if you want. Like I can wait for some time. We have time. So I can wait for some time. You guys can go ahead and try this. And if you're facing any issues, we can discuss. Check what? Check the part. Check. I can give you guidance right now. Yeah. So if you have doubts, I can give you guidance. So if it's explanatory, you can write like here what I'm doing. I'm sampling 10 steps and checking that. So that you can write. Like it's just simple comments which make the code explanatory. Like if some step is like you can try to make the code more readable and so that whoever is grading can understand that. So I can come with it. So, the code lines you can mention that there is a that line, yeah, yeah. I think most of that if they are self-explanatory, then it is fine. Yeah, yeah, I think it's okay. Like for this, it's not much commenting is required. Yeah. So I can show you last time we did some experiments on Hofding inequality. So basically, Hofding inequality is something similar to a Chernow bound, which also bounds something like this. So it says the deviation from the mean to be greater than some epsilon is this probability is less than this number or this expression when we are taking n samples, capital N samples. So here we wanted to do the same thing. So, but this we wanted to do for, we wanted to run Monte Carlo simulations to verify this inequality for a binomial distribution of known probability. So binomial distribution is different from a Gaussian distribution. Uh, so here we could just sample out from binomial distribution and then we would generate plots. So let me just try to run this. So yes, and then go back. Yeah. Yeah. So this is how the simulation looks like. This is a continuous simulation. So I'm running for all the n's. So in a continuous range, not the discrete values that are given in the experiment. And for each n, we are calculating the probability. So we have so many numbers here. That's fine. That's for each n. But for the current assignment, we'll have numbers for the given n's which are there. And we can also have a continuous curve. So you need not run for continuous values here, but this is an example plot for Hobding inequality. Yeah. So I guess this is fine. If someone is trying, I can have a look, or we can jump to part B as well. So for part B also, you need not use the code template which is given. So this is, you can make your own, write your own code from scratch, and you need not use, but this is like a guideline which you can use as well. You can use parts of code which are given in this. If you're using code for somewhere else, you have to cite it properly. But make sure you don't like lift the whole code for whatever is asked. Okay. So yeah, so let's go through it. So basically this uses gymnasium, which is generally used for environments, creating environments in RL simulations. And there are other things which we'll use here for plotting and for basically iteration. This displays the number of iterations and all. And then we have, then we import those things here. So this is the basic setup that we use for, so let me just run this. So I guess everyone is familiar with multi-arm bandit problem. So I'll not dive into it. So we have multiple arms basically. Let me give you a brief. Yeah. So we have a slot machine which has multiple arms, and we can pick each arm is associated with a stochastic reward, which comes from some distribution which is unknown. And we basically pick any one of the arm and we get a reward out of it. And then we repeat this process and we try to figure out what are the reward estimates for each of the arm for picking up the best possible arm for maximizing our cumulative rewards over multiple steps. Yeah. So that's what we want to create, an environment, a bandit environment. And in this setting, this example gives an implementation for a Gaussian bandit environment in which the reward comes from the Gaussian distributions for each of the arms. So for each of the arm, you have a mean and you have a standard deviation from which you get a stochastic reward. So you pick up an arm, and then for that, for that arm, you get out of that reward which is sampled from the mean and standard deviation. So basically, this class is inherits from this gym environment class, and then we have here. So this basically creates an environment in which you have multiple. Zoom in. So you basically have multiple bandits and multiple experiments. So imagine going to a casino where there are multiple slot machines. So when you create that class, you basically create a casino in which there are multiple slot machines. There could be machine 1, machine 0, machine 1, machine 2, and multiple machines. It depends on how many you want to create. You can use that. And then you basically create, each machine will have certain number of arms, which you can pull out of. Selecting this and this are the inputs to the class. So it depends on, so basically when you are creating the environment, it has an init function. So init function, you give the mean and standard deviation. So mean and standard deviation is a 2x2 matrix. So basically you give it, so this is a mean matrix is a 2x2 matrix, not a 2x2. Basically it is a matrix with number of arms cross number of environments, or basically number of environments cross number of arms, whichever, like however you represent that. So this is the mu matrix, and then you will have a sigma matrix, standard deviation matrix, which will basically be again the same. Here, number of bandits cross number of experiments. Okay. So whenever you are getting a reward for any action, suppose I want to pick an action, I want to pick arm 3 across all the slot machines. So basically then I'll sample from this mu comma sigma vector, which is this. So this will be the mu vector, and this will also be the sigma vector. So this is for the third arm, say, then I'll be sampling from this mu. So my mu will be from here and sigma will be from here. And these will be the corresponding vectors. So suppose if my action is across all the machines, is from the first machine, I want to pick arm 1. From the second machine, I want to pick arm 3. From the third machine, if I want to pick arm, say 4, then again 0. If suppose this is the scenario, then I will pick the corresponding, sorry, not this. So I'll pick the corresponding ones. 1, 3, 4, 0. And then I'll pick these corresponding means and create vectors, and then I can sample rewards from them. Right? Is this clear? Is this not clear? Okay, then I'll again explain it more clearly. So basically, whenever we are creating a ARM Bandit environment, we are basically creating multiple machines in the environment. These multiple machines are basically different slot machines in a casino. And there are multiple arms which have multiple arms. So we can pull an arm from each of the machines. This can be different. So just consider simple. There are two machines, M0, M1, and there are two arms, 0 and 1. Okay. Now, when I create this environment, this is the environment which is created now. Here, this is defined by, there will be, each machine will have a mean for, reward mean for each of these, right? Like this will have a reward. Say if I pick arm 0, I'll get a reward from 10, 0.1. So this will be my reward. If I pick this, if I pick arm 1, then I'll get maybe 0, 0.1. And from machine 2, if I pick, I may get a reward here as 0. And this standard deviation could be 0.5. And if I pick again from machine 2 arm 1, I may get a reward of 5, 0.5, say. So basically, these are my distributions for each of the arm. So my mu matrix will become 10, 0, 0, 5, right? And my sigma matrix will become 0.1, 0.1, 0.5, 0.5. Right? So Now, if I say I want to pick arm 0 from both the machines, what I will do is I will take 10, 0, and I'll take sigma as 0.1, 0.5. So I'll pick these entries. And then I'll sample from this variable. This will give me some reward of picking arm 0 in the environment for both the machines. Correct? I'll get a reward from this only. So I may get some reward, say 9.9 and 0.1. Right? If I sample from this. So this one sample could be like this, right? If I want to pick, if I pick, say, arm 0, yeah. If I pick arm 0 from machine 0 and arm 1 from machine 1, then this vector would be 10, 5 and 0.1, 0.5, right? So this will be then I'll sample from this. Correct? So now generalize this to more machines and more arms. Simply. So I'll have a mean and a standard deviation matrix, which will be arms cross number of machines. And then basically whatever action I take, I'll pick the corresponding entries from the matrix. And then I'll sample from those vectors, corresponding vectors of means and standard deviations. I guess that is clear now. Are there any doubts with that? So that's what we try and implement in the code. We define the number of bandits, number of experiments. Number of experiments basically the number of machines which are there. The action space is basically number of bandits because that's the number of possible actions that we have for each machine. The observation space is basically discrete. So we initialize this with this environment with a mean matrix and a standard deviation matrix. This will define the environment. If I want a 2x2 environment, my mean will be a 2x2 matrix and my standard deviation will be a 2x2 matrix. If I want more number of bandits, then I'll increase that. So then it will be 2x4, then it will be 4 bandits, 2 machines. Then similarly, standard deviation will also be 2x4, right? That's clear, right? Okay, now let's go ahead. So this is basically how we initialize the environment. This is like for a Gaussian environment because we are sampling from a Gaussian. Here the environment is Gaussian and we sample from Gaussian random variables. You could change it for other, I guess the question demands you to have it from a different. Because we are defining these variables according to that. So this will be clear. This will be clear once we go ahead in the function. Okay. So we already saw how we were sampling rewards from the particular arms, right? When we pick a particular arm, how we get the reward. So that's how we want to simulate. So a step function here basically tells you, takes you a step in the process. It's basically taking an action. So if I want to take an action, I give an action to the step function. And then the step function would basically give you reward. So step function returns basically observation, reward, if the environment has terminated or not, if we are in a terminal state or not, and some information which regarding the process. So this is the standard gym structure which is followed, or gymnasium structure which is followed. And we'll try to follow these in the coming assignments as well, because this is how it is structured. So I will encourage you to use this template, because this is how we will code. The further assignments will also be there. And this is the standard practice for running RL simulations. Like, this is how the gymnasium environments are designed, where you'll get this sort of if you take a step function, you'll get the observations, rewards, and if it's a terminal state or not. So when we'll go to the next part of the course, where we'll study MDPs and other things, there you will understand this further, that how this is, because now for bandits we only have one state. Like, you end up there only. So there is no other state. Nothing changes there. Your estimates for those rewards changes, but then the bandit remains like that only. So the environment doesn't change. There is only one state. Okay, so now let's go ahead and see a little bit this function. So what happens in this function? The same thing happens what we discussed in the text. So basically, whatever action you want to take, you find those means and standard deviation vectors based on that action. So here I'm picking those means for which for the arms that I want to pick. And then I basically sample a reward vector from that. So this is the same function that we saw earlier. We sample from this mean and the standard deviations, and the size is the number of experiments. So I'll get a reward vector. So this is a reward vector for all the machines. Yeah. So if I have 10 machines, I'll get a 10 cross 1 vector. Yeah. So that will be returned. Okay. Yeah, I guess this is fine. Anybody has doubts with this? Okay, let's go ahead then. So there is another function here, which is like, if you don't want to give mean and standard deviation, and you want that to be assigned randomly, then we basically have this class, which is arm bandit Gaussian class, where the means and standard deviations are assigned. So basically, the mean is sampled from randomly selected, and then the standard deviation is just 1 for all the arms and over all the machines. Yeah. All right. So let's see this in action. So if we have, I think it will be more clear through an example. So let's go through the example. So here we have a mean and standard deviation array. So this, basically, we have only one machine here. So how many bandits are here? Anybody? Yeah. We have 4 bandits, and we have only one machine. And now we basically create this environment class by initializing it through this mean and standard deviation. And now what we want to do is, we want to pick all the arms one by one and see what reward we get. So we'll just pick each arm one by one and see what reward we get. So let's do that. So when we pick bandit 0, we got reward 6, which justifies because its mean is higher. For others, we get lower rewards. For this, we get a very high reward because the standard deviation is very high. So it could be anything. So let's sample again and let's see what we get. So again, we got for this high reward, and for this, again, it's close to 0. Okay. So now let's add another machine to it. Let's see what happens. So let's add an identical machine. It has the same mean and same, we can change that also, or you can play with it, you can experiment with it. Now I'm picking the same arm in both the machines. I can change these means and standard deviation also. Like we can make it -5. We can make it +10. We can make it -1. Okay, now so now we are getting a reward, which is like for both the machines. For the first machine, we have this reward for the second machine. And these are for picking the same arm in both the. So you could pick different arms also, but here I'm picking the same arm. If I add another loop and I do I comma j, then it will just pick different arms. So you can see how we sample rewards from this. Now, once we are able to sample rewards from this, what we can do is, so here we know this mean and standard deviation. So we know which arm is the best arm, right? So which one is the best arm in the first machine? Yeah, first arm. And the second machine? The last one. Yeah. So here we know. But generally, this is the property of the casino, right? This we don't know when we visit a casino. So how we have to find it out? We have to find it out by sampling. So we sample multiple rounds, and then now we have to find out through the sampling process. So we basically sample and we get this reward. And then from this, we have to figure out which are the best arm. So from one sample, can we figure out? We cannot figure out because maybe we can figure out from one sample, but we don't know. So there are various algorithms now for doing that. Now, how do we evaluate our action? So one is like we take running mean of it. We take mean of it multiple times, and then we say, okay, this is the average reward that this arm is giving. So this arm must have a higher average reward. So that we can do. So we have a function for calculating incremental average or incremental mean. This is pretty straightforward. Like we have a set of numbers. The direct mean calculation is this, but we can also do it through an incremental average. Right. So I guess this is fine. Let's go ahead. So this incremental average we can use. We can use when we are sampling and we get samples, and then we can calculate incremental average, and then we can update the means of those. Okay, let's go ahead. There is another function, which is an helper function, which is given to calculate argmax. So argmax is basically, we want to now sample what? We want to sample what, like in class, we must have studied greedy algorithm, right? So greedy algorithm does what? It calculates or samples the best arm known so far. So whichever arm we know is the best so far, it will pick that arm. So so best so far means from our knowledge, from the agent's knowledge. So agent's knowledge will be some estimate of the means of the estimates of the rewards, right? Or from which estimates we are getting the rewards, right? So from that, we can basically pick, the greedy algorithm will pick the arm which has the maximum estimate currently. Okay. So for calculating max, we can use this function. What this function does is it will calculate max, but two arms may have same reward estimate as well, right? So we want to break tie between them. So what it does, it adds a small noise to it, which is randomly generated. And then based on that, whichever gets a higher random noise, we pick that. So it's just an helper function. Then now let's now code the greedy agent, which we know. So greedy agent, what will it have? It will have reward estimates. So agent will keep track of whatever rewards we are getting. And it will keep a matrix of reward estimates. This matrix will have the same size as the number of arms cross number of experiments or number of machines. So for each machine and for each arm, it will try to keep an estimate of what is the mean of the reward function which it has. So that's what we want. So similarly, how we define the class, arm bandit class, we have this class which has an initialization function which uses this reward estimates. And this reward estimates is basically initially could be 0. We could define it initially could be 0. So that's what it's defined to be, I think. No. So this is how we initialize it. And there is another function in this class of greedy agent, which is get action function. So this get action function picks the best arm, which is arc max. So you could see that over all the machines, it will pick the arm which is maximum. So it just pick the maximum argument which has the maximum value, and you will get an action. And this action can then be, so what it does is it picks that action, and it also has an action counter. So action counter is basically, it will count how many times each of the arms have been selected. So initially this action counter will have same matrix, and it'll add 1 to whichever arm is picked. So action counter will initially be 0 for all. So that's how we have defined here. And it has the same shape as reward estimates. So let me just briefly explain here. So basically this greedy agent, this has reward estimates. This reward estimates is basically another matrix, which is the agent's understanding of how the casino is. So it will have basically its number of bandits cross number of machines or experiments. And then it will also have an action count. So this action count is basically, again, the same thing. This will just count the number of actions which have been picked by the agent so far. Why we are doing this? We are doing this so that the agent can update its rewards after each action taken. So if I take some action in the environment, I can now update my reward for that. And that reward can be updated by using the incremental mean. So basically, so how do I update my reward estimate? So I get a reward and I know what action I have taken. So now I basically select what action I have taken, or this. So I take the action count. So this gives me the action that I have taken over all the machines. I have previous reward estimates for those actions, and then I basically update only those entries of the reward estimate matrix using this incremental average. So this is the simple thing which we are implementing is this here. So basically we are implementing here. So earlier we had a reward RN for a particular hour. So earlier we had this estimate for the particular hour. Now we got a reward RN, and using the incremental average, we update its current new estimate to be using this equation. So that's what is implemented here. All right. So any doubts at this point? So I encourage you to go through this further. And if you at any point of time have any doubts, you can reach out. You can reach out to me. We can discuss this further. Okay. So let's run this, and now we want to test this agent. Now we have designed the environment. Once we have designed the environment, we have designed some auxiliary functions which will help us to design the agent. Then we designed the agent as well. So this is an agent which will act on the environment. And now let's go ahead and test this. So for this experiment, we have two machines. So basically, it has two machines. So there are two experiments, and there are 8 bandits in each of the machines. And we want to run for 100 steps now. The mean and standard deviation are randomly selected. So we are randomly selecting the mean and standard deviation for the environment. These are not known to the agent. These means and standard deviations are the properties of the environment and are not known to the agent while taking a decision. If this were known, the agent would easily pick, right? It will pick just argmax of this and it will always get the best thing, right? We can test that also. We'll test that as well. So now we initialize the environment with those means and standard deviations. We create the greedy agent. So the greedy agent's initial reward estimates are 0 because it may not have any understanding of the world. So it doesn't know anything about the environment. So better to initialize with zeros, right? Because if we initialize with something, then we don't know what will happen. So we initialize it to 0. And then we want, so basically this is just a helper function to visualize. And we take multiple steps in the environment and plot. So I'll not go into detail of the helper function, which is there. And we can discuss if anyone has doubts with that. I'll just run this and let's check the simulations. To run for multiple simulations. Let me run this again. Yeah. Yeah. So you can see here that the greedy agent picks. So here the greedy agent picked this arm, and now it's exploiting this arm alone. Here it took multiple actions, but got negative rewards. So it wanted to explore further because it was getting, and it ended up with this one. So here in this case, it got the best arm. But here it missed out on the best arm because the best arm would give it reward of around 2, but it got stuck with this only because it always selected the greedy action. We can run this again and check. See what happens. Yeah. You can see that the greedy agent generally gets stuck at one arm. You can try this like in your own notebooks as well. Yeah. Now we can try to run this for numerous experiments, for 10,000 experiments, because we have general function. We can do it for multiple steps, and we can change the number of bandits because those are flexible. And then what we want to do is we want to see how many times on an average the agent selects the optimal arm. The greedy agent selects the optimal arm. So we want to run simulations. So there are we are in this part of the code. What we are doing is running simulations for multiple experiments. And again, these are sort of Monte Carlo simulations only. And we are selecting in how many of those things the agent selects the best possible arm. So optimality is basically the percentage of times it selects the best arm. So we see that it's less than around 40% or something. Right? So it selects the. So now let's go ahead. Let's see, let's try to change that agent or modify it a bit to see if we can do a little bit better. So you would have studied this Epsilon-greedy policy as well. So Epsilon-greedy is like act greedily most of the time, but certain number of times you act uh, randomly. So that randomly times where you are acting randomly, that helps you explore a bit. You can go to other arms as well. So how do you code that? How do we code that? So Epsilon greedy agent will be initialized with similar reward estimates, same as the agent which greedy agent, but you also have an epsilon parameter. Now this epsilon we can tune and it will basically regulate how much the agent explores. If this epsilon is 1, it will always take random actions. If this epsilon is 0.5, it'll half of the time it will take greedy action, half of the time it will take random action. Now, how do we code that? So get action is something which we have to change the function. So what we do? So action type is basically, yeah. So here we just select what type of action it is. So what type of action it is basically for each of them, we randomly sample, we generate a random sample. If that random sample is greater than epsilon, then it's basically random action or an exploratory action, or sorry, a greedy action. So so we basically just have this action boolean, which will either take a greedy action or an exploratory action. And for an exploratory action, we just pick any random arm over all the experiments, over all the machines. And again, it will just update the action count for them, whatever actions are taken here. Yeah, everything else is same for this class. So now let's go ahead and try to see what the epsilon greedy agent does. So this is again for 2 experiments, 8 bandits, 200 steps. We are running this again for now this is for epsilon greedy agent. Okay. And what is the parameter for it? It's 0.1. So 10% of the times it will explode. Yeah. So let's go ahead and see. Yeah. So you can already see that it's more exploratory. It's going to other arms and trying to explore further. Yeah. So it sort of covers all the arms, even at 10% of exploration. Yeah. Run this again and check. Yeah, basically that's the idea. So now again, let's run an experiments to see how many times it takes the optimal action, similar to last time what we did. And when we run this, we see that the epsilon greedy agent with 0.10% exploration does far better than a greedy agent. And this reaches around 80%. So 80% of the time, around 1,000 steps, it takes the right action. So it's 80% optimal. Now we can test for various values of epsilon. You can run this for multiple values of epsilon and again check which value of epsilon works best. All those experiments we can do. And basically again here 0.1 is better than other values that we have selected here. Yeah. So yeah, that's sort of it about the demo. For the question now, yeah. So for the question now that we have familiarized, we want to create a simple environment. So now you can choose to use the base code or not. It's up to you. You may or may not. It's fine because this environment which is given here is quite simply. You only have uh, two bandit, and it's not a Gaussian bandit, it's Bernoulli bandit. And you have means given there, and the means are different by this value delta. And we have to run for distinct time steps. Yeah. So the first part of this is we have to take delta as 1/4 and run Monte Carlo simulations to estimate the expected regret of the ETC algorithm. So ETC algorithm is explore then commit. So ETCL agent would be very simple. It will be like what you do is for first few time steps, you just pick all the arms or pick all the arms randomly. That also you could do because uh, for if n is that exploration period is sufficiently large, then you are almost guaranteed to pick all the arms, or you can pick them one by one as well for uniformity. And then after that, you do greedy approach. Pick the best possible arm after that exploration step. So for this, what we want to do is we want to choose M to be order of this times before committing, and then we want to find this regret. So we calculated optimality. Regret is something which is close to optimality. It's just that the best arm is now we know is mu2, and whatever reward we get, we just subtract from that. So we can write code to find this regret, and then we can repeat this multiple times to see what happens. Yeah. So for this part, you have to write the code. For the other part, we have to run it for various deltas and do this step again. And once we are done with this explore and commit, then we have to do it for UCB algorithm. The same thing. So UCB algorithm is upper confidence bound. So we have a confidence bound on both the arms. So we pick the one with the higher confidence bound. So it's simple. It's just a variation of the greedy one, the UCB, where instead of the mean, you picking the mean from the argmax of the mean, you pick the argmax of the upper confidence bound. Yeah. So go through this. There is a lot of time you have. Like this is due on 4th. The second part, it's more rigorous than the first part. First part is quite simple. So you can finish that straight away and then directly move on to this B part. And then if you're facing any doubts, any issues, we can discuss. If you have any doubts now, we can go through that as well. Anybody has doubts online? Okay. So I think that's it from my side currently. If there are any doubts, you can reach out. The details are shared of me of all the TS, and my details are also there, so you can reach out to me. And yeah, I'll be staying back. If you have any doubts, we can come and discuss as well.
सत्या क्या कह रहा था उसका लड़का लग गया